All right. So what you saw is we're looking at the something called orbital elements. Okay, and you have to have 6 unique orbital elements to, or 6 elements to uniquely define an orbit. Okay. So where did we start? We started at the equatorial plane. We started with the equatorial plane and the ecliptic plane. What is the ecliptic plane? Ecliptic plane or the orbital plane. Okay. So the 2 planes meet at a line, and that line is called the line of nodes. If you see there, that's the line of nodes. You can actually access this on NASA's website if you want to look up. It's space.
Yes, included those terms in that. Those
Yes, all those terms. They might be a little different, but they'll be there. Okay. For example, periapsis may not be there in that.
what else can be called?
It's called perigee
Okay.
in the astrophysics. So perigee is specific to Earth. Periapsis is a general term. Then there is perihelion or perihee. If you look at the terms, there is perihee. The central body is Sun. Okay. So this line of nodes is the line of intersection of the 2 planes, and this line of intersection, because there are 2 planes, this ecliptic plane or the orbit is actually it's the circumference of that plane. Right? You understand circumference? Close your cell phone. Okay. So the circumference of the plane is the orbit. You understand that? Circumference of the plane? The circumference of this plane, the orbital plane, is the orbit. The orbit itself is a circumference. The orbital plane is a plane which includes that circumference. Okay? So this point on the circumference is the ascending node. And the opposite point on that same circumference is the descending node. Because from this point forward, what's happening is the orbiting body is ascending. It's going above the equator. It's climbing up the equator. And if you go on the other side, from that point onwards, it is going down. It's descending. That's the reason it's called descending node. Okay? Now you define line of nodes, you define ascending node, and you define descending node. Okay? Now, the other thing we define is, we define this reference frame, ECI reference frame. To define any reference frame, let me get to it.
I got a little one, I don't know.
Plus. Thank you. The reference frame you always need at least 2 directions to define a reference frame. Okay? The third direction will simply be the cross of the 2 directions. So what we do is we define this vernal equinox. We discuss this vernal equinox in detail, right? On the first day of the spring, line passing through the center of the Earth and the 0-degree longitude. Make sense? So you define 2 directions. You define first is x direction. Okay? X direction is vernal equinox. We use the symbol this damn symbol. This is the Aries. Vernal equinox, the direction is the line passing through the center of Earth through the 0 degree longitude along the equatorial plane. Because this line can pass from North Pole to South Pole, right? Anywhere. It has to, so this we have to make sure it is passing through the equator, equatorial plane. Okay. Look up this vernal equinox. Vernal equinox direction. Vernal equinox is what? Vernal equinox is a specific day.
January.
Yes. It's a specific day. So there are 2 equinoxes and 2 solstices. I told you, right? So September 23rd was autumnal equinox. And then we have vernal equinox, which is first day of spring. Okay. And between then we have winter solstice. And then between vernal equinox and autumnal equinox you have summer solstice.
And what's the Aries that you wrote underneath?
So what happens is, if you look at this, along the equator, all your 12 constellations are actually along the equator. The star signs we have, all those are constellations. Okay, constellation of stars. Aries is one of the constellations with this symbol. This symbol is also associated with, actually the constellation does look like that. The stars are in that constellation. If you draw this line through and through, it goes through this Aries constellation.
If you draw what line?
So the line connecting the center of Earth and the 0 degree longitude on the first day of spring, going through the equator, if you keep going, it will go through the Aries constellation. You understand? Where is the Aries constellation? So if you look around the equator, it is all these constellations are actually on the equatorial plane. There are many more constellations, of course. There are hundreds, thousands of constellations, right? But these constellations are along the equator. That is the reason we have. So your constellation, your sign, your birth sign is because that thing was passing, when you were born, that thing was passing through a particular constellation. Okay? That is the reason you will have certain characteristics. Now we have defined this, so we have defined this x as this direction. Now we define the z direction as well. Okay? Z direction is simply the axis of rotation. Axis of rotation of Earth. And this is always the same axis of rotation in the right-handed sense. Okay, this is the axis of rotation if Earth is rotating in this.
Okay, to clarify, understand everything you said except what is passing through. I don't understand what's passing.
You said something was passing through when we were born. That's the question. When we were born, something was passing through.
That axis is passing through another constellation.
What axis?
So you're listing that axis on the first day of spring. That axis is passing through. If you are born on the first day of spring, you belong to the Aries.
So the
Aries.
vernal equinox.
Right. Vernal equinox is a day. It's a day on first day of spring is vernal equinox.
Okay. So
This is the vernal equinox direction.
So are you saying the x-axis is passing through?
This Aries constellation.
Okay.
Goes through the Aries constellation on the first day of spring. So everybody born in January in this thing, they are supposed to have Aries star sign. Is that true? Probably. But that is actually true. So that's what we have. Now the z direction is simply the axis of rotation. Okay? This axis of rotation is always the same. Does it change? It may change. It will never change. Right? Unless it is wobbling. You understand?
The rotation of Earth will never change?
The axis of rotation, will it change? Probably not in our lifetime, right? Not in several of us.
What's the probability?
Huh?
What's the probability?
It's not a problem, it is a deterministic problem. It's not a problem, it is a known thing.
Okay.
That's the momentum.
No, at least we actually.
See, what happens is, when it is rotating, what happens if you keep rotating something? The mass seems to accumulate more at the equator. Right? If you keep on rotating something, the gravitational pull it's like this, right? And if it is rotating like this, there is more. It tends to oblate. There is oblateness in Earth. What does that mean? That the poles are flat. They are actually flat. Poles are supposed to be considered to be flat compared to this. So that is when you can say the axis over the relative axis may change over billions of years, okay, or thousands of years. But for all practical purposes, we say z direction is always fixed, and y just completes the right-handed. It is just z crossed with. Okay. So you can say these are all unit vectors, right? Alright. So now if you look at this, this is the, okay, let's start with orbital elements. Okay. We start with A and E. A is what? So if you're looking at here, what is A? A is, if you look at this, the distance or the measurement from this point here, look there, from this point to this point would be what? 2A. Right? It's the major axis. A is semi-major axis, 2A is major axis. It defines the size of the orbit. It's very similar to conic section. A defines the size of the orbit. Okay. What does E define? E defines the shape of the orbit. Right? We looked at this very clearly. What is E for a circular orbit? 0. What is E for an elliptical orbit? Less than 1, greater than 0. What is E for a parabolic orbit? 1. Okay. And what is E for a hyperbolic orbit? It's greater than 1. Okay. So this defines the shape. You understand? Size and shape.
Oh, they're both size and shape?
This
Or
is
is
size.
shape? Yeah.
This
and
is
that's
shape.
Okay.
Then you have these angles. This is right ascension. It's also this short form is often used. Right ascension of ascending mode. Okay. This is cap omega, and it is the angle between x direction and ascending node direction. Okay, and this is always in this angle is measured in equatorial. Angles can be measured as long as you're, or for the purpose of, as long as you're in this program, I don't think you learn 3D angles. Angles actually can be measured in 2 planes. Okay, but we limit our scope to measurement of angle in just in a single plane. You need something?
Yeah, did you discuss that? You need us to give it back to you, or can you take
Yeah, I need it back. Okay, so this angle, you can see this angle is actually measured in the equatorial plane. Okay, huh? This cap omega, you see it is measured in the equatorial plane. Alright. The next one is angle I, which is called the inclination. How do you measure the angle between 2 planes? If I tell you this is one plane, and if I say this is another plane, right, like this, how do you measure the angle? Can you measure an angle between 2 planes? Angle is not defined for 2 planes. But you're actually measuring, if you actually try to measure, you'll measure angle between 2 lines. Right? So this thing, although it is the inclination is the inclination of the orbit with respect to the equatorial plane, the measurement is made with respect to the perpendicular to the plane. So what is the perpendicular to this plane? This equatorial plane. It is the axis of rotation is the perpendicular. Okay. And this on H is the perpendicular to the orbital plane. The angle between these 2 planes is the angle between Z and H. Make sense?
So it's not the plane itself. It's
the same thing.
So why do you say you couldn't measure angle?
You don't technically measure angle between planes.
So the
angle is not defined between planes. Angle is always defined between.
okay. So the H is perpendicular to the
orbital plane.
Okay.
Right? You see that? And C is perpendicular to the equatorial plane. H is actually, you know what H is here? It's the angular momentum vector. angular momentum vector. So we have said, we often say that, right? The momentum vector coming out. That defines, angular momentum, what does it define? Angular momentum vector will always define the direction of motion. Just like axis, the z direction defines the motion of Earth's rotation. Angular momentum vector will define the motion of the orbiting body. You see that? In the right hand itself, always in the right hand itself. This is the age, right? What is the direction of motion? It's going like this. If considering or assuming that's a prograde orbit, if it's a retrograde orbit, what would the motion be? The opposite direction. Then the angular momentum vector would be the opposite direction. Then the angle would be different. Right? That is the reason you cannot define angle between two planes. Angle between two planes could be this or this. Right? But when you do this, it will always be exactly between two lines. It takes into account the motion, the direction of motion as well. Okay. The next one is small omega. This is called argument of periapsis. Or argument of periapsis. Okay, and this is angle between ascending node, ascending node and perigee. This is the angle between ascending node direction and the perigee direction.
What do you mean by argument of the periapsis? What does that mean?
That's what it is called, argument of periapsis. This angle, each of these angles have a name. So the name of this angle, cap omega, is called right ascension of ascending node.
So the argument part doesn't really mean anything to the name.
It also means, so this is it's the angle between the node and the perigee direction. You see where it is going, up to what point. It is going up to the point of perigee.
Okay, so it's just a name. It doesn't have any meaning.
It does. This periapsis of perigee. You see the angle. Can you see the angle? Where that angle goes from?
The red line. The red line.
Yeah, it is up to the direction of
The perigee.
perigee, starting from where this cap omega ends. Huh? Right. It's from ascending node to the. So it's actually argument means something like that.
Okay.
Okay. So this cap small omega, you see that? It's angle up to this point.
And where is the periapsis on there?
Periapsis would be
The perigee.
this, right?
Oh.
Okay. So if you want to look at it from the top view. So this is the x direction. This is the right ascension of ascending node. If you see, this angle is actually completely measured in the equatorial plane. Gray part is the equatorial plane. Okay, and this argument of periapsis is measured in the orbital plane. This is the top view. Making sense?
What's the two axes we were talking about? Periapsis and what? What's the other one?
The apoapsis.
The what?
The apoapsis.
Apoapsis, where is that on there? Is that not on there?
It will be in there. The apoapsis would be what? What direction would be apo? This is the periapsis, right?
So it'll be the other way, right?
Yeah, it will be here.
Okay, so the exact opposite.
Now these three angles together define the orientation of orbit. Okay. And there is finally in the figure you are going to see this as V0. It's the true anomaly. It defines this is the angle between the perigee direction and position vector.
Oh. Theta is equal to V9.
Theta is V0. So the orbiting body, let me zoom here. Okay. Where is the, if you see, that's the orbiting body. Okay? So it keeps on moving, right? This orbiting body is in motion. This angle, this is V0. It's the angle between the perigee direction and the position vector of the orbiting body. Again, that has to be measured in the orbital plane. Make sense?
What has he measured in the orbital plane?
This angle, so there are, see this size and shape, then there are three angles which will give you the orientation of the orbit. There is one angle which will give you the position of the orbiting body with respect to the perigee direction, periapsis direction.
But then you said that one of those is measured in the
This angle is measured in the equatorial plane. This angle is measured, this is the angle between the planes. This angle is measured in the orbital plane. This angle also has to be measured in the orbital plane. Right?
Can you define anomaly?
Anomaly is what is anomaly? Anomaly is unknown.
Okay, so that means it's a true unknown pattern.
True unknown. It's the unknown in the sense it's always changing.
Okay, so it's an unknown, always changing
Right.
pattern.
So it's the anomaly is you can say it's true angle. The theta is actually an angle.
But we just don't know this.
We don't know because it is changing.
Changing.
It's an unknown parameter. It's something you determine.
Okay.
Right? All these parameters for any given orbit, these parameters will always remain the same. You agree?
1 through 6 will remain the same?
1 to 5 remain the same. 1 to 5, it's like, think about this. If you want to uniquely define a row, you will need these. Okay? you consider a racetrack, right? Racetrack will have a size, racetrack will have a shape. Got it? Racetrack will have an orientation. What does that mean? Racetrack can be, you are trying to measure the orientation with respect to a particular plane. Okay? So racetrack could be like this, could be like this. It can change its orientation in 3 degrees. Just like you can change the position in 3 degrees of freedom, you can change the orientation about this axis, about this axis, about this axis. This defines that orientation with respect to what frame? X, Y, Z, the ECI frame. This frame is fixed, right? The equatorial frame is always fixed. But this is unique for these 3 will define the orientation of a given orbit, or the orbit of interest. This will be different for the space station. It would be different for what would be the orientation of a geosynchronous orbit? What would be the inclination of a geosynchronous orbit or a geostationary orbit? What is the inclination of a geosynchronous orbit? Geostationary orbit? Huh? Geostationary orbit? Huh? There is no inclination? It's 0, right? Why is it 0? It is in the equatorial plane. It is actually in the equatorial. Geostationary orbits have to be equatorial orbits. You understand that?
They have to be equatorial orbits?
Yes. Can US have a geosynchronous orbit, a geostationary orbit?
So you can what?
Can US have a geostationary orbit?
Like the US?
United States of America?
No.
You're not in the equator. So you cannot have United States cannot have a geostationary orbit. But if you look at what are the countries which are along the equator, only those can have a geostationary orbit. What is a geostationary orbit? It's like something goes up there and it is useful to you, right? It's not like you cannot have. You can have, but it will not be of use to you. If you put a satellite in a geostationary orbit, it will not gather any information from your location, right? Because you are off of the equator. You understand? But there could be a geosynchronous orbit. What is geosynchronous and geostationary?
One more time, geo what?
Right. So geosynchronous, geostationary is always geosynchronous. Right? Geostationary is always geosynchronous. Geosynchronous is not geostationary.
It moves at the same. What is
The period of what is the period of Earth's rotation? It's 24 hours, right? So if something is moving at 24 hours, it will be geosynchronous because the time periods are synchronized. Geostationary, it is moving at the same time plus it is always there. The relative position does not change. Right? If you want a satellite, all the satellite networks or your satellite TV, it has to be a geosynchronous or a geostationary satellite. It has to be always there.
So to
get your signal.
The geostationary isn't orbiting.
It's orbiting, but it's orbiting at the same speed. So if it's like this, Earth is moving and it is also moving at the same speed. Plus, it is on the equator. Okay? So geosynchronous is not necessarily on the equator. It can be anywhere.
And it's not moving at the same speed.
Geosynchronous is always synchronous is always moving at the same speed. The orbital period is the same.
not along the equator?
It's just not along the equator. So you see how these parameters define an orbit? So if you have, think about this. You may have the same racetrack, okay, for many vehicles. But this will uniquely define the position of that vehicle on the racetrack. That is the reason this value is so important. Because without this, see, unlike racetrack, without a car, without a vehicle on the racetrack, will the racetrack still exist?
Yeah. There's no true anomaly.
Huh?
There's no true anomaly.
There is no true anomaly. But is that true for an orbit? Without an orbiting body, does an orbit exist? It does not exist, right? Without an orbiting body, there is no orbit, it's just space. So that is the reason this makes that orbit. When something goes up there, that traces that orbit, that imaginary track. Got it? So you can have all of this. Okay? You can have two orbiting bodies on the same, exactly the same orbit. Correct? Where one is following another. So what will change in that case? This will change. Got it? If you have
When you have two orbiting bodies in the same
right,
orbit.
right. If you have, think about this, okay? So you have one orbiting body here, one orbiting body here. Okay? All of these parameters are the same for both these, except that theta. That theta is, this is the theta, theta 2. This is theta 1. Got it?
So
So
you
that's
said everything else is the same?
everything else can be the same. The size is the same, the shape is the same, the orientation is the same, but these are considered two different orbits. Got it? These are actually two different orbits because theta is, huh? Because theta is different.
And speed.
Huh?
Speed.
Speed will be the same. If the orbit is same, the speed has to be the same. You cannot speed up and still be in the same orbit. If you speed up, what is going to happen?
I thought it was speed up to stay in the same orbit.
No, if you speed up, you'll just. So for something like this, if it's the same, that is Kepler's third law. The time period is proportional to the distance. Okay. So that means the speed, if you are in the same orbit, this will never catch up with this.
So they're going at the same speed.
They will always have to be at the same speed.
So they'll be at the same distance. So
They will have to be at the same distance. Being in the same orbit, you can never catch something. Okay? If you speed up, what is going to happen? It's going to go on a bigger orbit. If you slow down, it's going to come inside.
We said those are two different orbits, though,
Those are two different orbits.
because it's true anomaly is different.
Full down these three. So all of these six uniquely define an orbit.
In a true anomaly is only the angle between, it's just the position of where they're at in the orbit, right?
It's the position of the orbiting body.
The position of the orbiting body, but they have the same one.
They have the same 5 elements.
Okay.
The size is the same, the shape is the same, the orientation is the same, okay? But their position is different.
Okay,
So that is the reason they are considered, they are said to be two different orbits. Because this is different.
So like they're the same orbit, but they're like on top of one another?
They are actually following, think about the racetrack. Okay, so everything is same. The road is the same, but where they are is different. That is the reason we say they are two different orbits. The road itself does not define an orbit. The track itself does not define an orbit. Where the position, where that orbiting body is with respect to this direction is the same again for both of them, the perigee direction. Okay? But this theta is different. Theta is different for this orbiting body, theta is different for this one. Thank you.